Hello, my friends, and welcome back to another exciting week here in GSC 109, or General Physical Science, and the accompanying lab, GSC 109L. So, this week, we are continuing our investigations. We are delving deeper into physical science phenomena, and we want to be able to understand a much broader picture. And that is where thematic section number 2 comes into play. And that's called the power within, exploring energy, mechanics, and electricity. But this week, we want to be able to grow our body of knowledge, our scientific awareness and literacy by transitioning from fluid mechanics, such as static fluids, or also known as fluid dynamics, and get into the hot topics. Yeah, that's right. For the next couple of weeks, we are going to learn about heat based properties. And we're going to first start off with thermal energy. Crucial role in the development of the Appalachian region, driving economic growth and shaping its industrial landscape. They connect remote mountain communities to broader markets, facilitating the transport of coal, timber, and other resources, which become vital industries in our region. Railroads also bring in goods, services, and workers, leading to the rise of towns and expansion of the local economy. In addition, they help integrate the Appalachian region into the national economy, contributing its industrialization during the late 19th and early 20th century. But here, deep in the Appalachian spine of West Virginia lies a small town of Cass, home to the world-famous Cass Scenic Railroad. The railroad is home to the world's largest collection of geared Shay steam locomotives, three of which we witness in operation on the CSRR along the geared Heisler steam locomotive number 6 Railroad's Whitaker trip. From there, we can also see and go for a ride as the Western Maryland Railway, also known as the Big Six, brings us to Bald Knob, one of the highest points in West Virginia. This week, we are conducting another investigation and introducing a new concept that I'd like to share with you because I find it is most fascinating when sharing physical science phenomena, especially because it relates to engineering. And that is the term thermodynamics. Don't worry, this isn't going to be just questions and dry definitions. We're actually going to break down thermodynamics in an easy to digest format with real world applications and examples. And even a touch of history and how these concepts power the world around us, give us energy so we're allowed to do work. But we have to ask ourselves a question. What is thermodynamics? Well, at its heart, it's the study of energy, heat, and actually work. It's how molecules move around in physical systems to help us in our day-to-day lives. You see, the word comes from the Greek using the words therme, which means heat, and dynamics means power. And basically, it's the science of how heat gives us power, and in this case, powers our lives. But we need to be able to break this down a little bit further. Energy is defined as the ability to do work. And we've probably already touched on this in the course so far. And work is when force causes something to move. And that's the key right there. Imagine pushing a train car down the tracks. Well, that's going to be a lot of work. Just thinking about that makes me feel tired. But energy, if we can use that and deploy that into that system, shows up and allows us to move that train car. It comes in many forms. We have chemical energy, such as energy found in the food we eat. There's potential energy, say in a stretched bow, or in some of our examples earlier in the semester when we worked on collisions. But most importantly, in this week's module, we will be utilizing thermal energy. Basically, energy that's going to be produced when something gets hot. Because heat is just energy molecules in motion, specifically a transference of energy. There are three main ways that we can allow this to happen due to thermal connectivity. There is conduction. Think of it like taking a metal spoon and heating it up if you leave it in your cup of soup for too long. There's also convection, the hot air rising and cool air sinking, commonly observed in other physical science phenomena like weather systems. There's also radiation. Radiation is the warmth we feel in our day-to-day lives, coming in from thousands of light years away, if not millions, as it travels through the vacuum of space to get to our planet. And allows us to feel the warmth on our skin without needing really any medium at all. A really great textbook example of how heat can be transferred. Now, like many scientific investigations that we have conducted in this course, module by module, I always like to delve into some of the history behind these wonderful scientific innovations. And our study in thermodynamics goes as far back as the 19th century, when we look at scientists like Sadi Carnot and Rudolf Clausius. They were pursuing technology to improve what we call steam engines. And this was considered cutting-edge technology at the time. They realized that no machine could ever be perfectly efficient in terms of work. And this discovery gave birth to the laws of thermodynamics that we will be using in our module this week to be able to communicate this scientific phenomenon of how heat transfers. These laws explain why your car engine naturally gets hot, why refrigerators and freezers work the way they do, and even have implications to our third thematic section this semester when we deal with astronomy and how stars burn in the depths of space. So now I'd like to share with you the laws of thermodynamics, utilizing some basic examples. Picture this. Let's say you brew up a hot cup of coffee. You put it on the table. Well, there are two laws that come into play using this example, and that is going to be called Zeroff's law and then the second law. Zeroff's law is the state of thermal equilibrium. Your coffee cools down until it reaches the same temperature as the surrounding air. And I think that's a great way to think of what we call equilibrium. And you may have heard about this term several times over the course of the semester. But then what about the second law? Well, heat naturally flows from hot to cold. The coffee loses heat to the air, and you never actually see the reverse happen. Your coffee never spontaneously just gets hotter and hotter and hotter just by sitting stationary. That is a term we call entropy. Energy spreading out and dissipating or displacing if you're thinking kinematics, because you can actually measure how the molecules will be moving. Let's reverse and go back to my very first example in this weekly welcome, the steam locomotive. It actually uses the first and second laws. In the first law of thermodynamics, the chemical energy is found in coal, which Appalachia is well known for. When we burn that coal, it's being converted into heat energy by burning. And then we take that heat energy and apply a media like water to get steam. The steam expands through pistons, and this converts heat energy into mechanical energy, and thus allows work to occur. And energy, because of the rules of conservation of energy, isn't created nor is it destroyed. It's just being transformed within a closed system, such as the steam engine locomotive. But going back to that second law, we can also make the scientific claim based upon the data gathered that no engine is 100% efficient. Some heat it has to escape through, say, the smokestack, but the metal walls of the boiler system or friction within the gears, that produces wasted energy. And that wasted energy also is entropic, our bodies. You see, I study biology, being a paleontologist myself, but our bodies have to maintain what we call homeostasis. And homeostasis in biology is the same as saying that there is an equilibrium occurring. It's why we stay healthy. But we can also apply those rules of thermodynamics within a closed system such as our body. And the first law states that when we look at our bodies and in the environment that we navigate, we encounter radiation from the sun, part of that heat transference. And the sun is just a giant nuclear reaction occurring out in space. But as it's releasing energy in the form of radiation, the energy travels through space and eventually warms our skin. Your body then takes the abundant energy also from food and uses both of those in conjunction to, say, power our muscles and allow us to conduct movement and maintain internal body temperatures. You'll notice that it is being passed along and transformed from one source to the next to keep our bodies running optimally. In the second law, we can think of it as the sun's energy being able to be entropic. And then we can also bring in Zerzoff's law. Well, let's say we stand in the sun long enough, we eventually have our body and skin and the surrounding areas reach a perfect balance, thus maintain that equilibrium. And that's one of the reasons why when we have the shade or the wind passing us by, naturally feels cool because our body's responding to that using that law of thermodynamics and wants to maintain a comfortable equilibrium rather than just sitting outside and burning. But then we have to bring in that third law. So when we have low temperatures, entropy approaches a minimum, and living organisms like us can't function at what we call absolute zero. And this is how it explains why life depends on a constant flow of energy that is thermal based, and that we have to be able to convert it to either being sun or food. Our ordered system of our body would collapse in disorder if we cannot attain that. So I think that is really relevant to our studies for this week because, again, our bodies are subjected to thermodynamics, but we can collect data to be able to learn more about it and use that knowledge to become more efficient, build more efficient machines, which physical scientists like to be able to develop because they're engineers to make our lives easier. Now, in conclusion, when we talk about thermodynamics, we're not just talking about, say, an abstract science. We're really, again, talking about how energy moves in the universe. From the simplest atoms to the largest galaxies, they are subjected to these laws. And over the next few lessons, we're going to also unpack on how these principles truly shape how we develop engines in life itself. So as always, if you have any questions about the module this week, please reach out during my open office hours. You can get a hold of me using email, you can set up a video chat, or just swing by my office in room 208, and let's work together to produce energy through thermal dynamics. You'll never look at heat the same way again.